We're finally ready to come up with our short and easy way to find areas under curves or evaluate definite integrals. And remember, these are useful not just for the sake of finding an area under the curve, as a very pure mathematician might be interested in doing, but because anytime we have any rate of change, finding the area under that rate of change curve tells us the total amount that the quantity changed. So again, if you have the rate at which a population is growing or declining, you find the area under that rate curve, and that will tell you the actual number of people that the population gained or lost in that given time interval. So it has very, very practical applications. So this is what we're trying to do. We're trying to compute the area under f of t from a to b. Suppose that we know our new word, an antiderivative, capital F. So for example, if this had been x squared, we know x cubed over 3. So we know a function whose derivative is little f. As usual, let our area function be starting from just some point c, it doesn't have to be 0 as we discussed, 2x of f of t, the same area function as we've been using before. So here's our graph of f of t. We would like to find this area. Before we can do that, let's note a few things. So we proved that, what did we prove in our previous theorem? We proved that a prime is little f. So since a prime is little f and big F prime is little f, that means both a and big F are antiderivatives of little f. So both a and big F are antiderivatives of little f. So how different could those two functions be? What did we say about that? If they're two antiderivatives of the same function, all that can happen is that one is a vertical shift of the other. So they must differ only by a constant. Thus, I can write a of x as big F of x plus some constant. I have no idea what the constant is, but that's not going to matter. We're going to see. We already know some function capital F of x. A of x is the function that's giving us trouble, right? It's hard to find the area under a curve. So I want to find the area under this graph from a to b. First, we want to write this using our capital A, our area function. So if I want to find just this little area from a to b, and the capital A function, I don't know why I keep calling it capital A, there is only one A function here. The area function here starts at c. How can I write the area between a and b in terms of my area function, capital A? I can say I find the area from c to b, this whole area, and then subtract off the area from c to a, just like we did in that previous example. So this will be capital A of b, that's the area from c to b, minus the area from c to a. But capital A is the function that we don't have a nice formula for. So we don't like working with that function. But we prove that its derivative is little f, and we say that we know another function whose derivative is little f, capital F. Therefore, we had this result. So what can I write here now? I can write a of b is the same as f of b, capital F of b, plus this constant. And a of a is the same as capital F of a plus this constant. And the constant has to be the same, right? If two graphs, if one graph is shifted up 3 units from another, it's shifted up 3 units everywhere, not just at some x values. So it's the same constant. So when we subtract, the constants cancel, and we get f of b minus f of a. And believe it or not, this is great for us. We'll see some examples in a second to show how great it is, because big F is the function that we know. That's the one whose formula we know. And a common way that mathematicians write this in shorthand is they write capital F of x, and then we draw a vertical line. Remember when we saw that vertical line back in Leibniz notation in week 4? What did it mean back then? A single vertical line meant evaluated at. So in this case, we put the a down here and the b up there, and this means exactly what we've written in the previous line. Plug in b, plug in a, and subtract. This is the fundamental theorem of calculus. So let's write it out in one nice box. And again, some people call this the first fundamental theorem or the second fundamental theorem. For me, it's the fundamental theorem. The fundamental theorem of calculus. it says that if capital F prime equals little f, meaning if you know an antiderivative of little f, that's all you need in order to find the area under little f. I'm going to use the letter x here, equals capital F of b minus capital F of a. Let's put that whole thing in one nice big box. It sounds important, yes? The fundamental theorem of calculus. Seems like something we should really pay attention to. If capital F prime is little f, then if I want to find the area under little f, all I need to do is plug in two values into capital F. Compare this to how we were doing things before with that example x squared. We need to look at all of those rectangles, infinitely many rectangles, all the way between 0 and 2. This says no, don't worry about all of those rectangles. All you have to do is plug in two numbers, not infinitely many rectangles. Just plug in two numbers and you'll get the answer. That is so much faster and easier and cleaner. And it's because we found this very important connection between derivatives and areas. So let's show this. Let's show off the power of this fundamental theorem with three examples. First, let's do the one that we spent so much trouble on and were only saved by this magic formula coming out of the blue. Not magic, it was a true formula. What does this say all we have to do now? We know the answer was supposed to be 8/3. That's what we figured out the long way. Here it says all I need to do is find an antiderivative. So we already found an antiderivative of x squared. We can choose any one we want, and we'll talk about why that is in a minute. But let's suppose we choose x cubed over 3. It says all I'm supposed to do is plug in the two numbers. So I'm going to plug in, I'm going to get 2 cubed over 3 minus 0 cubed over 3, which is 8/3, exactly what we got, but it took almost a whole chalkboard, at least, to get it back then. Look at how easy it was here by the fundamental theorem. What if you had chosen a different antiderivative? What if you had chosen the one that was x cubed over 3 plus 6 here? Would you have gotten the same answer? Yes, because there would have been a plus 6 here, and then minus this quantity with the plus 6, so the 6's would have canceled. So in practice, we write the simplest antiderivative, the one that has a plus 0 at the end. But if you're feeling frisky, go ahead and write plus whatever your favorite constant is there, because it will cancel out and you'll get the same answer either way. In this case, 8/3. I hope you appreciate how much faster that was. And that was because we found this very, very crucial connection between areas under curves and derivatives. So the only way we were able to get this is because we already knew derivative rules. Similarly here, this is saying find the area under 1 over x from 1 to e. And as we mentioned before, if we tried to do this the long way using the Riemann sum and infinitely many rectangles, we would get stuck at the point where that formula came in to rescue us before. There is no way to get past that. But the fundamental theorem says we don't need to worry about any of those rectangles. All we have to do is say, do we know a function whose derivative is 1 over x? So can you think of such a function? Do you already know one whose derivative is 1 over x? Yes, you do. Natural log of x. Again, you could put plus any constant that you want there, but we don't need to. And it says all we have to do now is plug in natural log of e minus natural log of 1. And what is the natural log of e? The natural log of e is 1. The natural log of 1 is 0. So look at that. The area under your most basic hyperbola, y equals 1 over x, from 1 to this number e, that seems to be popping up again, is exactly 1. Isn't that nice? In fact, this is a way that a lot of people will define e, to say that start at 1, keep going until you get an area of 1 under this curve, and whatever x value you've gotten to, that is e. And that definition of e we can show is equivalent to the way that we defined e using a limit the very first week. But look at that. Very nice, clean answer from that. Do you know any other fundamental theorems, by the way? Do you know the fundamental theorem of arithmetic, for example? Fundamental theorem of arithmetic says if I take any positive integer greater than 1, I can always write it as the product of prime numbers. So what would this be? 2, 2, 3, 7. And it says there's only one way to do that, meaning there's no way, for example, that I could replace the 3 and the 7 by some other prime numbers. There's a way to do it, and it's unique. There's only one way to do it. This is called the fundamental theorem of arithmetic. It tells us that if we want to build up the positive integers, we do that by multiplying primes. So primes are the building blocks for the positive integers. And in particular, this shows us why the number 1 is not prime, right? Because if 1 were prime, I could put times 1, and I would have a different way of writing this. But there's supposed to be only one way of doing it, according to the fundamental theorem of arithmetic. There's also the fundamental theorem of algebra, which is most commonly seen in using complex numbers, which we're not really talking about here yet. But if you're talking about just a normal polynomial, it says that a polynomial of degree 8 can have at most 8 roots, 8 solutions when you set it equal to 0, and that if it does have, if you're allowing for complex solutions, it will have exactly 8, allowing for some repeated roots. Let's do one more here. Sine of x. So before we did the sine of x, the integral from 0 to 2 pi, and that worked out to be 0 because we saw that the things above and below would cancel. But how about this? What if we just look at one arc of the sine curve? What should that equal? How much area should there be under just one arc of the sine curve? Well, we don't need to worry about drawing all those rectangles and taking the limit as n goes to infinity. We just need to say, can you think of a function whose derivative is sine of x? Does any function come to mind? Must be something with a cosine of x, right? But if I just put cosine of x there, what's the derivative of cosine of x? That's negative sine of x, right? So how can we fix that? We put a negative there, because then the derivative of negative cosine of x is negative negative sine of x. So at the moment, we're just sort of doing a little bit of guess and check to come up with these antiderivatives. In our next week, we're going to make a list of all these antiderivatives that we already know. And the reason that we already know them is because we know the derivative rules. I hope you're realizing that we're getting these almost for free. The reason that I know this is because I already have a derivative rule. So let's do this. So now we plug in the one on the top first, negative cosine of pi minus negative cosine of 0. Pi means you're all the way around on the other side of the unit circle. So the cosine there is negative 1. So that's negative negative 1. And the cosine of 0 is 1. So that's 1 minus negative 1, 2. The area under one arc of the sine curve is an integer. It's not just a rational number, like, say, 13/6. That would be pretty cool. But it's an integer. It's exactly 2. There's no reason to expect this to happen. This could just as well have turned out to be pi over 17, or some completely inscrutable decimal that goes on forever, some irrational number. But it's not, because the area under this piece of the sine curve works out to be exactly 2, and the fundamental theorem of calculus is what allowed us to figure that out. I hope you take a few moments, or more than a few moments, to appreciate this fundamental theorem of calculus and this very intimate connection between areas under curves, which is our new project, and slopes of curves, which was our project for most of the semester. This says that if you know a rule for finding a slope, you can undo that rule and find an area. Who would have ever have guessed that these two would be so closely linked together, finding the area under a curve and finding a slope of a curve? It's not at all apparent, at least it wasn't to me, that these should be connected. And that basically, if I know how to do one, I know how to do the other. It's like saying if you already know how to multiply, you basically know how to divide as well. Here we're saying if you know how to take the derivative, you know how to find the slope of a curve, then you also know how to find the area underneath a curve. And we'll talk more about this in our next week's video. And for now, we have a check your understanding so you can practice using this fabulous and wonderful fundamental theorem of calculus.